And welcome to basic limit properties. So the idea here is we have seen ways we can find limits to approximate limits, but always graphing or always always plugging in numbers and evaluating can be long and tedious. So we want a faster way to find limits. So again, are two ways of approximating limits. Can be long and tedious, or just require graphing equipment. Require technology. So it would be nice to have some ways to evaluate limits without approximating, just algebraically. Or nice to actually evaluate limits algebraically. So before we get into that evaluation, just so we want some basic properties that will allow us to generalize as we learn our new different ways to evaluate. So just some key facts here. Let's say that B, C, L, and K are all real numbers. So our real numbers, we have C is a real number, C is a real number, L and K are both real numbers as well. N is an integer, we'll see N in a bit. And F and G are functions defined on an open interval I, which contains C. So we have an interval along X, and along there we have the interval I. We have the function F and G defined on that interval. So here's F and G. And then our C is somewhere within that interval F and G are defined on. And then again, we have that the limit as x approaches C of F is equal to L, and the limit as x approaches C of G is K. So we have a variety of statements. So first up, we have for constants that the limit as x approaches C of the constant function B is simply B. So for example, the limit as x approaches 2 of the constant function 5 is simply 5. So if we graphed that, the constant function f of x equals 5 would be graphed as a horizontal line at y equals 5. So as we go in from the left and the right, as x goes to 2, y is going to be 5. The identity we have the limit as x approaches c of the function x is simply c. So for example, the limit as x approaches 2 of x is said to be 2. So if we look at a graph of the function f of x equals x, we're looking at the equation y equals x. So here's 2. And as our x values approach x equals 2, the y values are approaching y equals 2. So since y equals x, it kind of makes sense that the limit would just go to whatever x value we are approaching. Some differences. We have the limit as x goes to c of f of x plus or minus g of x, depending on which one we are doing. Turns out that this is just the limit as x goes to c of f of x plus or minus the limit as x goes to c of g of x, which I believe we said these were L and K, if I remember correctly. Yes. So basically, if we are adding or subtracting two functions and trying to take that limit, we can simply split the limit across the addition or subtraction and evaluate the two limits separately. Next up, we have scalar multiples. So this is the limit as x goes to c of b times f of x. This is the same thing as b times the limit as x goes to c of f of x. So in this case, that would just be b times whatever that limit was, which we defined it as L. So for a specific example, let's just do the limit as x approaches 2 of the function 5x. So this is 5 times the identity function. We were just looking at the identity function in number 2. So this is just 5 times the limit as x goes to 2 of x, which we had previously said that is simply 2. So this is 5 times 2, or 10. So again, going from this to here, that was the identity. Next up, we have products. So the limit as x goes to c of f of x times g of x. Turns out just like we could split a limit across addition and subtraction, we can do the same across multiplication. This is simply the limit as x goes to c of f of x times the limit as x goes to c of g of x, or in this case, L times k. So for another example, let's consider the function x squared, looking as x goes to 2. So x squared is just x times x, and we already know how to take the limit of the identity function, f of x equals x. So we can split this as the limit as x goes to 2 of x times the limit as x goes to 2 of x. And that just becomes 2 times 2, or 4. So again, we are using the identity to make this step. Next up, we have quotients. Just like our limits split across multiplication, they also split across division as long as the denominator is not going to 0. So we have the limit as x approaches c of f of x over g of x as the limit as x approaches c of f of x divided by the limit as x approaches c of g of x equals L over K, as long as K is not 0. So this is important. That limit doesn't exist or may not exist if K is 0. There are certain situations where it still does exist, but it's not guaranteed. So for example, let's take the limit as x goes to c of the limit as x goes to 2 of, let's just do the function x over x. We'll be boring here. So this is the limit as x goes to 2 of x over the limit as x goes to 2 of x. And then that, of course, is 2 over 2, or 1. Next up, we have powers. So for this, we are taking n as an integer. Then the limit as x goes to c of f of x, take that whole function raised to the nth. We can do the limit first, and then raise to the power. So again, exponents are just repeated multiplication or possibly repeated division if we have a negative exponent. So this is just using rules 5 and 6 can make this one happen. So in this case, this would just be L to the n if our limit as x approaches c of f of x were L. So for example, let's do the limit as x approaches 2 of x to the 5th. So here we are taking the identity function x and then raising that function to the 5th power. This is precisely the same as doing the limit as x approaches 2 of x and then raising that limit to the 5th power. Again, we know that this limit is 2, and raising it to the 5th power, we get 32. Next up, we have roots. So again, we'll take n to be an integer. And we will only pick c in the domain of the function. So we're looking here at roots. So we're looking at the limit as x goes to c of the nth root of f of x. And here c has to be within the domain. So remember, if we are taking even roots, this thing inside has to be positive, or at least, sorry, it has to be non-negative. So C has to be within the area that F is defined. Then this is the same thing as taking the nth root of the limit of f of x, or taking the nth root of L. So again, as I was just mentioning, we need for we need f of c to be within the domain, and in fact we need f of x in the domain of the nth root function near x equals c. Right. So for example, let's just look at the limit as x goes to 2 of the, let's do of the cube root of x. So cube root, we don't have any issues with what's inside. We don't need to worry about the domain. And we are looking at the cubed root of the limit as x approaches c of x, x approaches 2 of x, or the cubed root of 2. And finally, we are going to look at compositions. So for compositions, we are looking at one function inside of another. So just like we were just seeing at taking the root real power of a function, we can also take compositions of others. So we're going to have to modify our rules a little bit. So here we're going to modify. So we are going to assume that the limit as x approaches c of f of x is L, just like we were using before. And here's our modification. The limit now we will do as x approaches L of g of x is equal to k. And the other key feature will be that g of L itself is equal to k. Then what we wind up getting is that the limit as x approaches c of g of f of x is k. So for example, let's say that we wanted to find the limit as x approaches 2 of, let's do x plus 3 squared. Then we can sort of split this up. This is a composition. We have a series of functions going on. We can take the limit of the inside first, and then take the limit of the outside. So let's first do the limit of the inside first, and then go from there. So if we focus on x plus 3, and just look at the limit as x goes to 2 of x plus 3. This is a sum, so we can go ahead and split it. This is the limit as x goes to 2 of x plus the limit as x goes to 2 of 3. First one is the identity, you simply get 2. The next one is a constant, so we get 3, and that inside is 5. Right? And now we can look at instead the limit as x goes to 5 of our outer function. So that inside is going to 5. The outside function is squared. So now we can go ahead and continue this. This is the same thing as the limit as x approaches 5 of the square function of x squared. So this is our inner function. We're doing a composition. So the function x plus 3 squared is the composition of is g of f of x, where our inner function f of x is x plus 3, and our outer function g of x is simply x squared. Right, so now we can focus on the limit as x goes to 5 of x squared, and this is just the limit. Oops, let me switch back to my other color. As x goes to 5 of x, that whole thing squared, or 5 squared, or 25 by the identity. So we can take limits sort of from the inside and work our way out, as long as each series of limits then holds. So this is what we have here. Our limit is just 25. The reason that we have our one sort of caveat of g of L equaling k is if we wind up with a constant function on the inside. So if our inner function is a constant function, or if it's constant near our x equals c, then g of x, when we go to take the limit, we're not actually coming in along x, we're stuck at whatever f was constant at. But as long as we have that and equals, then we can just continue on through. So that is just some taking limits. This kind of allows us to work with any polynomials we like, and we can go ahead and evaluate the limits that way.